Moving on with probability, we're going to take a look now at Bayes' rule, section 4.5. Bayes' rule is very confusing. I was very confused by it the first time that I saw it. You're going to see some examples done here, and a lot of it might be really difficult to conceptualize at first. Hopefully, the more you see of these problems, the more you'll start to pick up on the pattern of how you solve them. So, the general Bayes' rule formula. Way of breaking down the conditional probability formula that we learned in introductory statistics. That formula told us that P of B given A, meaning we know the thing after the given line, A has already happened, equals P of A and B, the probability that both occur at the same time, divided by P of A, the probability that A has happened, because we know, based on this given line, that A has already happened. What Bayes' rule does is it substitutes into this formula to create a more complicated version, which allows you to solve problems you could not solve otherwise. What it works out to is the same thing that we had above. P of B given A equals P of B and A over P of A, same way we had it here. But now we're going to substitute in for each of these parts. What we're going to say is P of B and A is the same thing as P of B occurring times the probability that A occurs given B. It's really just a reordering of this original formula for conditional probability using, instead of B given A given B. So this all equals to this top, P of B given A. It's written as P of B times P of A given B. On bottom, all of this stuff adds up to the probability overall that you get A. Most of the Bayes rule problems that I'm going to give you, there's only going to be two things to break it down into. But Bayes rule doesn't limit it to that. Basically, on bottom tells you all the different ways that B could occur, either as B1, B2, B3, B4, up to what they call BK. Again, normally for the problems that I'm going to do for this level course, it's just going to be B1 and B2, two possible outcomes on bottom, where if you take the probability of that outcome occurring times the probability that A occurs when that outcome occurs, this tells you every time that A occurs with B1, plus this tells you every time that A occurs with B2, plus so on until we cover all the different B events, which means overall, when I add all these together, it's all the different ways I can get to A with the total probability of A. Again, a lot of this should sound like nonsense. It's a lot of letters, not a lot of numbers right now. But the hope is, as we work through these problems, you'll start to see what this formula really means and how to use it. So I'm going to work through 3 example problems in this PowerPoint. Then when we get together in group work, we're going to work through some on our own. Again, it should seem confusing, but do the best you can to try and pick up on the pattern, how I'm breaking things down, how I'm figuring out what goes where. The way that I'm really doing it is I need to first identify what A and B are explicitly. In other words, I need to label. For this problem, I'm going to call this event A. For this problem, I'm going to call this event B. Sometimes I'm going to label them with different letters based on what the question is asking, but I need to fit it to the original formula based on where A and B are in that formula. Decode the paragraph to find the 4 probabilities needed to complete a Bayes rule problem and identify them using the proper notation. Fit the probabilities to the general Bayes rule formula, and solve for the numerical answer. Solving for the answer can be a little tricky as far as making sure you have all the parentheses right, but again, it's going to be a pattern. When we pick up on how to put it in right the first few times, you'll be able to do it in the future. So I'm going to show you on this PowerPoint the problems done out in their entirety a couple different ways. First way I'm going to show it is with this example with MP3 players. A company manufactures MP3 players at 2 factories. Factory 1 produces 40% of the MP3 players. Factory 1 produces 60% of the MP3 players. And Factory 2 produces 40%. 2% of the MP3 players produced at Factory 1 are defective, while 1% of Factory 2s are defective. An MP3 player is selected at random and found to be defective. What is the probability that it came from Factory 1? So we know if something came from Factory 1, there's a 1% chance that it's defective. This is asking us if we already know it's defective, what's the chance that it came from factory one, which is the opposite of that. This is a much more difficult question than it appears. In order to do it, we're going to need to break it down using Bayes' rule. So what we're going to need to break down is this first choice, which factory it comes from. If we choose that it comes from factory one, that happens 60% of the time. If we choose it comes from factory two, that happens 40% of the time. As decimals, that means P of factory one is 0.6, P of factory two is 0.4. The next thing we know is that if we are sure it came from factory one, then there is a 2% chance it's defective. So probability it's defective given it came from factory one is 2% or 0.02 as a decimal. If 1% of factory twos are defective, that means probability of D are defective given that it came from factory two equals 1% or 0.01 as a decimal. We found an MPV player defective. What's the probability it came from factory one? To figure that out, we set this up. So seeing it as a tree diagram, we can see that we have this first choice where it's either factory one or factory two, 0.6 for factory one, 0.4 for factory two. Then we have this choice defective or not defective, 0.02 for defective, 0.98 for not defective. For factory two, 0.01 for defective, 0.99 for not defective. When we go to set up the probability that it came from factory one given it's defective, well, on top, we need the probability that both are occurring. The probability that both are occurring equals the probability that it came from factory one, which here on this branch is 0.6. I put in here for P of I, 0.6. Then we need the probability that it's defective given it came from factory one. The probability that it's defective given it came from factory one is given to us as 0.02 or 2%. So the overall probability that it's both defective and from factory one are these two numbers being multiplied together. It's anyone that followed this path on the tree that went first factory one with 0.6 probability and then defective with 0.02 probability. So on my top of my fraction, the probability of both things occurring that are within this conditional statement is 0.6 times 0.02. On bottom, I need to repeat that 0.6 times 0.02 because on bottom, what I'm really looking for is the total probability of what happens after the given line. In this case, the total probability that I get something defective. So the total probability that I get something defective is the probability I get something defective from factory one, which we found as this branch on the tree, probability from factory one times probability of defective. That has to be added to the probability that I get a defective from factory two. If I follow that branch to defective, it's the 0.4 chance it went to factory two times the 0.01 chance once it was in factory two, it became defective. So that's why I'm plugging in here for the probability of factory two, this line in the branch, 0.4. For the probability it's defective, this line, the 1%, 0.01. So we get on bottom, the total probability of getting a defective is this that represents the probability of getting a defective from factory one, plus this, the probability of getting a defective from factory two. Everything would need to go in there with proper parentheses, where I have a parentheses around the top, 0.6 times 0.02. I put in my division symbol. On bottom, I have outside parentheses, 0.6 times 0.02 plus 0.4 times 0.01, end parentheses. If I put that in properly to my calculator, it should tell me 0.75. In other words, there's a 75% chance that if something is defective, it came from factory one. A lot of numbers going in here, a lot of things to keep straight. Again, let me go back and show what it looked like as a question. So this is the way that it would be presented to you on online homework or on a test. It would ask a company's manufacturers MP3 players at two factories. Factory one produces 60% of the MP3 players and factory two produces 40%. 2% of the MP3 players produced at factory one are defective, while 1% of factory twos are defective. An MP3 player selected at random and found to be defective. What's the probability it came from factory one? I like students to start at the end and really figure out what's the probability question that they're asking if I want to do it in letters. So here it's asking what's the probability it came from factory 1, and we know an MP3 player is found to be defective. So the thing we know has already happened is that it's defective. What's the probability that it came from factory 1 is what we want to figure out. We want to figure out what's the probability of factory 1 given that it's defective. This is one of the hardest parts of this process. If you can break down this last part and say, here's what they're asking me, here's how I can represent it in letters, you can then use that to figure out, all right, what do I need to plug into Bayes' rule? If I know that I'm looking for the probability that it came from factory 1, and I know for sure it was defective, then I can know that I'm looking for factory 1 given defective, that I'm trying to find the total probability of defective on bottom because it's what comes after the given line, and then I'm trying to find the probability of both on top. Let's look at another example. A friend who works in a big city owns 2 cars, one small and one large. 3/4 of the time he drives the small car to work, and 1/4 of the time he drives the large car. If he takes the small car, he usually has little trouble parking, and so is at work on time with probability 0.9. If he takes the large car, he is at work on time with probability 0.6. Given that he was on time a particular morning, what's the probability that he drove the small car? So we have a few numbers here that we got to pull out. Specifically, there's 4 numbers that we're always going to need at least, maybe more if there's more than one alternate possibility. In this case, we only have 2 cars that he can take, the small car and the large car. We only have 2 outcomes that can happen. He's late or he's on time. There's only 4 total numbers that we're going to need here. The first number is this 3/4 of the time that he drives the small car. I'm going to write that as P of S. P of S is 0.75 or 3/4 as a decimal. If I wasn't sure on that, I could do 3 divided by 4 to get the 0.7. 1/4 of the time he drives the large car. 1 divided by 4 gives me 0.25, or 0.25 is the P of L, P of driving the large car. If he takes the small car, he has little trouble parking, so parking is easy. He gets to work on time with probability 0.9. So that tells me P of on time given small car equals 0.9. If he takes the large car, he's at work on time with probability 0.6. That tells me P of on time given large car equals 0.6. The last thing I need to do is decode this sentence, and really maybe it would have been easier to start here. But what this tells me is given that he was on time particular morning, what's the probability he drove the small car? So what we know has already happened is that he was on time. What we're not sure is the probability of S that he drove the small car. That's why I have to write it as P of S given line on time, or I'm going to call that T. So we're looking for the probability of S given that T already occurred. Showing what that looks like when we put it in the formula. We set up S equals friend drives small car. L equals friend drives large car. T equals friend is at work on time. P of S was given to us 3/4 of the time they drive the small car, so P of S equals 0.7. P of L is the probability of driving the large car, which is 0.25. The probability that he's on time, given that he drove the small car, is 0.9. The probability that he's on time, given that he drove the large car, is 0.6. We're looking for what's the probability that he drove the small car, given that he was on time. That really equals the probability that he's on time and drove the small car over the total probability that he drove the small car. We break that down further and say the probability that he's on time and drove the small car is really the probability that he drove the small car times the probability he's on time when he drove the small car. Click the head by accident. So we were told the probability of driving the small car was 0.75. That's where the 0.75 comes from. Then we were told the probability that he's on time when he drives the small car is 0.9. That's where this 0.9 comes from. The top of the equation is 0.75 times 0.9, the probability of being on time when you drive the small car. Then On bottom, we have to take that same thing that's on top. That's always going to be the first thing that we're adding because that's always part of the larger probability of being on time, which we're looking for here, or being defective, which we were looking for last time. But we also need the probability that he's on time when he drives the large car. Well, that probability can be found as the probability of driving the large car, P of L, 0.25, times the probability that you're on time when you drive the large car, P of T given L, 0.6. On top, when I multiply 0.75 times 0.9, I get 0.675. On bottom, this same calculation gives me that same 0.0675. And then when I do 0.25 times zero point 0.6, I get 0.015. This is showing step by step how the calculation goes. You'd be fine to put this whole thing in your calculator if you put it right. But this is more explicit, showing step by step how it's going to look. So on bottom, it's adding together both probabilities of being on time if you drive the small car and large car. When these two get combined, I get 0.825. This 0.675 is the probability that you're on time with the small car. If I take that out of the total probability that I'm on time, I get to the correct final answer of 0.818. Last example here, at a certain gas station, 40% of the customers request regular gas, 35% request unleaded gas, and 25% request premium gas. Of those customers requesting regular gas, only 30% fill their tanks. Of those customers requesting unleaded gas, 60% fill their tanks. While those customers requesting premium, 50% fill their tanks. If the next customer fills the tank, what's the probability that regular gas is requested? So this is a situation where instead of only having two options, like our factory one, factory two, our large car, small car, we have three different possibilities. Again, Bayes' rule can accommodate as many possibilities as they are. They list them up to A, so there could be 100 different things in a Bayes' rule problem. I would never give you one that difficult. It's way too much tedious math to deal with, but I do want to show you what it looks like when you have more than one. I believe there's at least one homework problem which requires you to have more than the two options, so in this case, three options. But the focus really is on problems like the two we did before. I just kind of want to show the extension, and it will be the case in this class. It's Stat 2, it's an advanced statistics class. We are going to be going a little further and into some more difficult, interesting problems that are a little beyond what I'll actually test you on, but are things I want us to consider and to work with within this class. So again, what we've been told, probability of regular gas 40%, unleaded gas 35, and premium gas 25. I don't even know if people do regular gas anymore. It feels pretty old, as did the MP3 players. Uh, we're going to pretend that it's a regular thing. If you want to say that this is going to be instead like ethanol instead of regular, we can do it that way. Either way, we have three different ways that people are getting gas. You can notice this adds up to 100% of the people getting gas. 40% plus 35 is 75, plus 25 is 100. Of those customers requesting regular, 30% fill their tanks. So given that they requested regular, the probability of filling is 30% or 0.30. Given that they requested unleaded, 0.6 they fill. Given that they requested premium, 0.5 they fill. But now we're not conditioning it on what they requested. We're trying to go the other way. We're conditioning it on we know the person fills their tank. What's the probability it was regular that they asked for? Again, we can't get there with the numbers we have unless we use this Bayes rule. Bayes rule tells us to break it down. We're going to list the possible events. The possible events, the three that we choose from, are either R, they select regular gas, U, they select unleaded gas, or P, they request premium gas. These are the three events that we're going to break it up into, and we're going to look at the chance that they fill their tank. So really, these are the different ones that take the place of A versus this is B. We know that P of regular, the first event, is 0.4. We know that P of filling it given that they're getting regular gas is 0.3. We know that P of unleaded is 0.35. The probability they fill it given unleaded is 0.6. Probability of premium is 0.25. The probability that they fill it given its premium is 0.5. We want what's the probability they got regular gas given that they filled. So in order to get that, we need the top to be the probability of regular and filled, and the bottom to be just the probability they filled the tank overall. This breaks it down further step by step until we get to this position where we say, all right, on top, I want the probability of regular gas. Probability of regular gas, 0.4, times the probability they fill it when they get regular gas. Probability they fill it when they get regular gas, 0.3. That's the whole top. This is the situation where they fill it and get regular gas. They chose regular gas, then they filled it once they chose regular gas. When I multiply these two together, I get 0.12, or 12% of the overall time is how often the person does both. But now we want to look at that out of the total number of times that somebody fills the tank. So the total probability of somebody filling their tank is the probability and they get regular and fill the tank, we already found on top to be 0.12, plus the probability that they get unleaded and fill the tank. Well, the probability they get unleaded and fill the tank equals the probability they get unleaded, 0.35, times the probability they fill the tank once we know they've gotten unleaded, 0.6. When I multiply these two together, 0.35 times 0.6 gives me this 0.21. The last thing I need to account for is the third possibility that they got premium gas and filled their tank. So we know the probability they got premium is 25% of the time, or 0.25, times the probability they fill their tank when they get premium. Probability of a full tank when they get premium gas was 0.5. So I take that 0.25 plus 0.5 to get this 0.12. I then on bottom add together all the different ways somebody could fill the tank to get the total chance that somebody fills their tank as 0.455. We knew the people who got regular gas accounted for 0.12 of that. If I take 0.12 divided by the total 0.455, it gives me 0.264. In other words, we know if somebody filled their tank, there's a 26.4% chance that they requested regular. So given that they filled their tank, the chance that they got regular is 26.4. Hopefully, as we continue to work through these, you'll start to feel more comfortable with it. But if you're confused now, I understand. Thank you for viewing this lecture, and hopefully I can help you with more problems like this and the ones that I'm asking you for homework when we look at them together.